The focus of this lecture is molecular orbital theory. So previously we talked about how oxygen is both paramagnetic and it has a double bond, and how there's no way to predict this using Lewis dot structures. And there's a figure in your book about talking about molecular orbital theory that illustrates the same issue. And so we need a better theory. So what we need is molecular orbital theory. And this is just an intro. This is just another picture of what molecular orbitals look like. And again, it's this delocalization of electrons that we've alluded to previously. Benzene's a great example. Benzene, you have electron delocalization over the entire molecule. It looks like a hamburger bun. It's kind of an amazing structure. And molecular orbital theory has a couple important parts. So first of all, molecular orbital theory is based on quantum mechanics. So it's based on the combination of atomic wave functions, or atomic orbitals, that combine constructively and deconstructively to form molecular wave functions, or molecular orbitals. So they're abbreviated AOs and MOs. Addition of atomic orbitals that is constructive interference will form bonding molecular orbitals. And this is when you have a region of high electron density between the nuclei. And subtraction of atomic orbitals forms an antibonding molecular orbital, which has a node or a region of free electron density between the nuclei. So this is just an analogy of a regular wave. So waves will constructively interfere, they'll reinforce, and will have increased electron density, or waves can deconstructively interfere, and they can cancel out where we can get a node. So if we have an increase of electron density between two nuclei, this is called a bonding orbital. But if we have a decrease in electron density, such as a node between our two nuclei, this is an antibonding molecular orbital. And this is a figure from the OpenStax textbook of two s orbitals that can either be in phase with one another, essentially adding together, and they form this bonding orbital. And I don't perfectly love the colors here because really I often do different colors or a line to show different phase, but really when they're adding together, they're constructively combining. So this should be maybe all one color. I think these two different colors make sense because they're different phases. So I don't know if this picture is perfect, but the point is that we have constructive interference like we showed here for our bonding orbital, and deconstructive interference for our antibonding orbital. So if we have two orbitals mixing, we always get two orbitals out. We have conservation of orbitals. So the bonding molecular orbital is lower in energy, and the antibonding orbital is higher in energy. And you can also determine this by the number of nodes. The bonding orbital only doesn't have any nodes, whereas the antibonding orbital has one node. And you also have conservation of energy. So however much more stable the bonding orbital is from the original atomic orbitals, the antibonding orbital will be that much higher in energy. Okay, so a molecular orbital diagram is just like an atomic orbital diagram. Remember we drew vertical atomic orbital diagrams. So molecular orbital diagrams are very similar, and I'll show you some examples of those in a second. But they just show the relative energy and the number of electrons in each molecular orbital. And the molecular orbital shows the antibonding orbitals from which each molecular orbital is formed. And we'll touch on bond order more in a little bit, but it's really important that you realize that we can use molecular orbital diagrams to determine the bond order. And the bond order is just equal to half of the number of bonding electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. So these are just a few more important rules. So electrons are placed in molecular orbitals just like they are in atomic orbitals. So they're filled by Aufbau's principle, Pauli exclusion principle, and Hund's rule. And if you're doing an electron configuration, you just give the name of the molecular orbital and the number of electrons in a superscript. So your steps for your molecular orbital diagram is first, you want to draw your valence vertical orbital diagram for each atom in your molecular orbital diagram. In this class, we're just going to do diatomic molecules just to give you guys a basic understanding. And then you're going to determine which orbitals mix. So in order for orbitals to mix, they must have similar energy and shape. Next, you're going to draw dashed lines showing the orbitals combining constructively to form bonding orbitals and deconstructively to form antibonding orbitals. And you're going to follow the rule that you have conservation of orbitals. The number of antibonding orbitals is equal to the number of molecular orbitals. And just like we mentioned previously, you're also going to fill up your electron configuration at the end for your molecular orbital diagram following Aufbau, Hund's, and the Pauli exclusion principle. And finally, you can use your molecular orbital diagram to determine bond order and paramagnetism. Okay, so here's an example of your molecular orbital diagram for hydrogen. So you draw your vertical orbital diagram for each atom first. So we've got one hydrogen atom here, one hydrogen atom here. This one's pretty straightforward because the 1s electron from each hydrogen atom is going to be at the same energy. So you draw a line or a box to indicate the 1s orbital for your first hydrogen atom and your 1s orbital for your second hydrogen atom. And these have similar shape and similar energy. So they're going to mix to constructively form a sigma bonding and a sigma antibonding orbital. And we can determine that it's diamagnetic. There are no unpaired electrons. And we can determine the bond order. So it's the number of bonding electrons minus antibonding electrons divided by 2. So that's 2 minus 0 over 2, which is 1, which is the same as what we predict for the Lewis dot structure for hydrogen. All right, so we could do the same thing for helium-2 and helium-2 plus. So you guys know that helium's doesn't like to form bonds with other things, and molecular orbital theory can help you understand this. So if you look on the right-hand side here, if two helium atoms try to bond together, it looks just like your hydrogen molecular orbital diagram, except for both of your bonding and antibonding orbitals are filled. So you have a bond order of 0. If you have helium-2 with a positive charge, then that means you're missing one electron. And now you have a bond order of 1/2. So that means your helium-2 with a positive charge is more stable than helium-2. Helium-2 doesn't want to form a bond at all. It's just going to this is not going to react to form this bond. So something that I don't think I mentioned is that when you're doing molecular orbital diagrams, you only draw the valence orbitals. So you only want to draw your valence shell in your vertical orbital diagram. So if we're doing lithium or beryllium, for example, we don't include the 1s orbitals. We're only going to include the 2s. So your 2s orbitals will combine constructively and deconstructively to form sigma bonding and antibonding. And then your 2s will do the same thing for beryllium. And you can see that the beryllium-2 is also not a favorable bond. And I really want you guys to think about the shapes of the orbitals. So if you have your s orbitals, we already talked about. They're bonding and antibonding orbitals. Let's go back to that really quickly. They form sigma bonding and antibonding. And we know this because it's cylindrically symmetric along the bond axis. P orbitals can form different types of bonds. They can either bond side to side and form pi bonding or antibonding orbitals, or they can bind end to end and form bonding or antibonding orbitals. We usually define this as the bond axis. We usually define it as Z. This particular figure is defining it as X, but usually in my classes I define this as the PZ axis. So if you were to look at all the diatomic molecules, molecular orbital diagrams from boron to neon, this is what it would look like. So boron, obviously we know that the electron configuration of boron only has 3 valence electrons. So total in our molecular orbital diagram, we're going to have a total of 6 electrons in our orbital diagram for diatomic boron. And we get our pi orbitals and our sigma. And the pi 2p are lower than the sigma 2p bonding for boron, carbon, and nitrogen. And then this is the so these are actually exceptions. This is the more common way that you'll see it. The sigma is both the lowest 2p and the highest energy 2p for oxygen, fluorine, and neon.